In the vast expanse of space, there are regions so dense and massive that not even light can escape their gravitational pull. These cosmic giants are known as black holes. Once something enters a black hole, it's gone forever. Or is it? What if I told you that black holes might not be eternal prisons, but rather temporary residents of the universe? This mind-bending idea was first proposed by Stephen Hawking more than 40 years ago. He suggested that black holes aren't completely black. They emit a faint glow due to a phenomenon known as Hawking radiation. But how does a black hole radiate when nothing can escape its grasp, not even light? To understand this, we need to delve into the bizarre world of quantum mechanics. At its simplest, Hawking radiation arises from the uncertainty principle in quantum mechanics, which states that we can't know both the position and momentum of a particle with absolute precision. Near a black hole, pairs of virtual particles pop in and out of existence. These particles have negative energy, keeping them bound together. One particle falls into the black hole while the other escapes. As the escaping particle carries away positive energy, the black hole loses mass. It may seem like a violation of the law of conservation of mass, but remember, mass and energy are equivalent. As Albert Einstein taught us, E equals mc, where E is energy, m is mass, and c is the speed of light. So the black hole loses mass, but gains energy. Let's do some quick maths. A black hole with mass m and radius r emits radiation with a temperature inversely proportional to its mass and radius. The smaller the black hole, the hotter it gets. This temperature determines the rate at which the black hole loses mass. If you want to see the math behind this, check out the references. The smaller the black hole, the faster it evaporates. A typical stellar mass black hole with a mass of about 30 kilograms and a radius of 295 meters would take almost 10 to the power of 64 years to evaporate completely. Now that's a long time. But compared to the age of the universe, which is about 10 to the power of 10 years, this is just a blink of an eye. So black holes can evaporate, but what happens to the information contained in the matter that falls into a black hole? This is where things get really interesting. The information paradox highlights a major difference between quantum mechanics and Einstein's theory of general relativity, which describes how gravity works. According to general relativity, once something crosses the event horizon of a black hole, it disappears from our universe, and all information about it is lost forever. But in quantum mechanics, information can never be truly destroyed. This apparent contradiction intrigued Stephen Hawking, who wondered if black holes might not be as mysterious and menacing as they seemed. In 1974, he made a groundbreaking discovery. Hawking found that black holes emit radiation due to quantum effects near the event horizon. This radiation becomes hotter the smaller the black hole. Black holes aren't completely black after all. They glow faintly, giving off light and other forms of radiation. As the radiation escapes from the black hole, it carries away energy, causing the black hole to lose mass. But here's the paradox. The radiation coming from a black hole appears to be random and carries no information about the matter that fell in. Yet quantum mechanics says that information cannot be destroyed. How can information seemingly vanish inside a black hole, only to re-emerge as meaningless radiation? Hawking suggested that perhaps black holes don't destroy information, but it remains trapped within the black hole until it evaporates entirely. At that point, the information supposedly returns to the universe in the form of Hawking radiation. Does that mean black holes don't actually evaporate? Well, they do, but incredibly slowly. For example, a typical stellar mass black hole would take nearly 10 to the 100 years to evaporate completely. This is much longer than the current age of the universe, which means that most black holes won't evaporate until long after the heat death of the universe. The information paradox has remained an enigma in physics for decades. It challenges our understanding of how gravity and quantum mechanics work. Some physicists believe that the answer lies in the mysterious realm of quantum entanglement. Others think that information might be preserved at the edge of the black hole in a region known as the firewall. In recent years, researchers have explored the possibility that black holes might not completely destroy information. Instead, it could be scrambled and encoded in a highly complex way. This scrambling could explain why the radiation from a black hole appears random and why information seems to be lost. But the exact mechanism for how this works is still unknown. Some researchers have even suggested that the information paradox might point to a flaw in our understanding of gravity. Perhaps gravity doesn't work the same way at the quantum level. Until we have a deeper understanding of gravity, the information paradox will continue to elude us. So the next time you gaze up at the stars, remember that black holes hold many secrets. They're not just cosmic abysses that swallow everything in sight. They're also laboratories for exploring the deepest mysteries of the universe. As we continue to probe the secrets of black holes, we're also probing our own understanding of reality. Because who knows? We might just find that the universe is a lot stranger than we ever imagined.